Okay, so let's start. Yeah, I'd like to comment on problems related to interpolation and approximation with multivariate polynomials and splines. So I'm a spline person. I always worked on splines, at a certain point, I wanted to use these splines for simulation and other advanced applications. And when looking into the theory, when trying to find error estimates, say for a finite element method with B-splines, I got the impression that some very basic questions in our understanding of the theory is missing. So I started to look deeper into spline approximation. And when I tried to do that, I found that even at an earlier stage, we have some problems. So even approximation with polynomials is not so well understood as you would expect for such a basic subject. Okay, here's the motivation for my talk. Modern approximation techniques like wavelet compression or things the like, they are widely used for audio or video data. Yeah, so this is commonplace, and they are used also for simulation on elementary geometry, or say images of elementary geometry, but they are rarely used for applications like simulation on general domains. And there are several reasons for that. To name just a few, I think that approximation is perfectly well understood on boxes. Perhaps not perfectly well, but rather well. It's partially understood on triangulations, and it's really not well understood on arbitrary domains. So questions like, how good can you approximate a given function on some subset of Rd? Yeah, problems like this deserve attention. Where do the problems come from? First, if you approximate with, say, tensor product splines or tensor product polynomials, and you have to realize some, say, homogeneous boundary conditions, then, well, this is not easy to do, but there are some tricks around, like the use of weight functions or Lagrange multiplier methods, but this is not so easy. This is not convenient. The second problem is related to the stability of the basis. This is one of the fundamental properties of the B-spline basis, but it's completely lost as soon as you restrict the B-spline basis to a subset, because there might be some basis functions with only a tiny little piece of their support inside the domain, and this is causing instabilities. Also here, we got some solutions, but also this is not trivial. And now, concerning theory, how well we can approximate with, say, tensor product splines on a domain omega. So omega will always be my domain. Then we have the following classical result due to Dahmen, DeVoe, and Scherer. It's 40 years old. The best approximation of a given function f by a spline S is bounded as follows. On the right-hand side, you see the pure partial derivatives in the coordinate directions, and you have the grid width, the knot spacing in this direction raised to the power ni, where ni is the order of the spline space in this coordinate direction, and then you have a constant. This looks like a perfect result, but there are two problems with it. The first one, the set omega has to satisfy very, very restrictive conditions. For instance, it has to be coordinate-wise convex, and. Many technical conditions. And the second, and perhaps even worse, problem with a constant is that this constant depends on the aspect ratio of the grid cells. So this constant is not uniform, but it depends on H. Okay, why would we like to use tensor product splines? Here you see a picture of a well-known old airplane with a very anisotropic structure on the surface. Yeah? So you would like to use different approximation spaces in this direction and in the transversal direction. Yeah? You would like to use low order splines in this direction and high order splines with a phi knot sequence in this direction. So tensor product splines are in many situations kind of natural, and sometimes they're really preferable to total order spaces, like you get for splines from triangulations. Okay, here's the outline of my talk. In the first part, I will comment on a very, very basic problem, the interpolation of functions based on a tensor product grid of interpolation nodes, and as interpolation space we use tensor product polynomials. In the second part, I will consider the problem how well you can approximate a given function on a subset of Rd on some domain, now with polynomials not necessarily in tensor product spaces, but also in more general spaces. And finally, a few shorter remarks concerning tensor product splines on domains. Okay, so let's get started with a very simple result. Everybody knows that. Given is a sequence of interpolation nodes on the unit interval. The interpolation nodes are denoted by gamma 1 through gamma n. And if the function to be interpolated, this function f, is sufficiently smooth, then the interpolation problem can always be solved uniquely, independent of the smoothness, of course, but the error estimate is reads as follows. The difference, the error, can be expressed that way. You all know that, yeah? So here it appears the nth order derivative at a certain point xi. And this is a very universal result. It also covers the Hermite case and also the Taylor case when all these interpolation nodes coincide. The proof is very elementary. So this is very fundamental. And to simplify this a little bit for further use, I abbreviate this leading term here by C of gamma. So the constant depends on the interpolation nodes, but you find a uniform upper bound, which is 1 over factorial n. And so this is first course in numerical analysis. Okay, what about the situation in the d-dimensional case? Yeah, so now we are on the unit cube in Rd. In this case, if you have simply a sequence of interpolation nodes, the problem is not always uniquely solvable. For instance, if all points are lined up, then of course there cannot be a solution. Also, the error is hard to express, it's hard to come up with formulas for the error. For polynomials of total order n, there is the Sauer-Hue formula from 1995, and in a paper by Carl de Boer on the situation with tensor product polynomials and also tensor product gridded data. So when all the interpolation nodes lie on a regular grid, he comes up with this formula. And Carl, with his special sense of humor, he says, this is an attempt to avoid more cumbersome notation. So this is, so I don't know how to decode this formula. And I asked Carl, and also he was some years later not able to explain me what this actually means. So I think something should be done in this context. So here is the problem now. The set of interpolation points has the structure of a regular grid. So it's the tensor product of these univariate sequences. Here you see the arrangement of interpolation nodes. In this case, of course, the interpolation problem is always uniquely solvable by factorization. You simply solve iteratively one dimension after the other, and you find the solution. But what about the error estimate? So if all partial derivatives of order alpha less than or equal to n, now is n a vector? You're in the tensor product case. N is the vector of orders in all coordinate directions. Then it's easy to find the following error estimate. Yeah, you see here certain partial derivatives and some constants, and the essence of this formula is easiest explained by means of an example. Yeah, so in the bivariate case, if you have order 4 in x direction and order 3 in y direction, then this error estimate reads as follows. You have the maximum of the fourth derivative with respect to x of the function divided by factorial 4, and the third partial in y direction divided by 3 factorial, and then you have mixed partial derivatives in this way here. So what is requested here is a derivative of very high order. So this is a derivative of order 7. Thinking of this Debord formula, we would expect that this last term should disappear. It should be not necessary. It's a uniform bound, but it requests high order derivatives. Can we get rid of that? Now, the proof for this formula is really very basic. You could give this as an exercise to a bachelor student. This is not difficult. It's essentially based on the commutation property of partial derivatives and the univariate interpolation operators and error operators. So this is fairly easy, but the result is not optimal. Okay, how can we proceed? How can we get further? Let me define the least distance delta of some sequence gamma of interpolation nodes. This is simply the minimal distance between two consecutive nodes. So this is delta. For instance, if you have Hermite interpolation, then you have a double interpolation node, and this delta would be 0. Now, there is a result by Atkinson, and also I myself, together with my PhD student Bernhard Mössner, we had a result in the following spirit. The approximation error, always measured in the subnorm, can be bounded that way. We have only the pure partial derivatives. This is the good news, but the factors in front of these partial derivatives include the Lebesgue constants of the univariate interpolation operators. You have these uniform constants, but then the Lebesgue constants of univariate interpolation. And it's important to note that the Lebesgue constant of an interpolation operator depends on the least distance. If delta, this least distance, is becoming small, the Lebesgue constant gets big. So this constant is again not uniform. In our simple example, the result is now the following. Now we don't have this high order mixed partial derivatives. In y direction, we have this nice behavior, third derivative and number. But in x direction, you see here showing up the least distance squared in y direction. So if in y direction some interpolation nodes are getting close, then this constant explodes. Of course, you can exchange the role of x and y, and then you have this result. Now the first, the x partial derivative is multiplied by a constant, but the y derivative sees now the least distance in x direction. So this result is also not perfect in a sense, and of course it's not symmetric. The interpolation process itself is completely symmetric, but the error estimate is not. The proof for this estimate is slightly more complicated. Let's say this is an advanced exercise for a master student, but it's also not so difficult. But there is one nice consequence of this result. If you are free to choose the interpolation nodes, then, as in many cases, it's the best choice to use Chebyshev nodes, so the zeros of the Chebyshev polynomials, as interpolation nodes. And in this case, you get the following nice result. It is possible to find a polynomial P, namely the interpolating polynomial at the Chebyshev nodes, such that the error is bounded in terms of the pure partial derivatives of f in the coordinate directions, and some factors which depend only on the order and the space dimension. So these numbers decay rapidly towards 0 if you increase the order. Okay, but if you are not free to choose your interpolation nodes, the situation is not yet understood in a satisfactory way. So what else can we do? I define now the least distance delta depending on m in such a way that m is the number of skipped nodes. So in my little example here, the m is 2, so I'm considering the distance between this node, and then I skip these 2 nodes, and then I take this again. So this is one distance skipping 2 nodes, and then I take this one, I skip 2 nodes, and I consider this distance, and now this distance, and this distance, and the least distance of this sequence, so that the least value of this sequence, this is denoted by delta of m. It's the minimal distance between a node and its m plus first successor. So in this case, if m is greater than 1, this delta of m is not necessarily 0 if 2 nodes coincide. This is used in the following way for a theorem. Given is n the vector of coordinate degrees. And now you can choose some vector m of integers, but such that it's in a sense not greater than n. So the sum of these ratios has to be strictly less than 1. If this is the case, then you compute the least distances in all coordinate directions with respect to the m values. So in the first coordinate direction, you choose the least distance skipping m1 nodes and so on through all the dimensions. And if all these least distances are bounded away from 0, so you find a lower bound delta bar, then you find this bound on the interpolation error. Then the interpolating polynomial p is such that the error is bounded by the pure partial derivatives alone, always of order nj in j's direction, and the constant is independent of the immediate least distances. Yeah. So if you find an m such that this is bounded away from 0, then you get the best possible error estimate. Let's see if this. Before I proceed, I'd like to mention that you find a very similar estimate if you consider derivatives of the error. Yeah? So the order of the partial derivative has to be again.
Excuse me, and what is R? What is R? Delta R?
Okay, this is just for all R from 1 through E.
Okay, so we can choose the best way. Yes.
All these distances have to be bounded away from 0 by this uniform constant, and then you get the estimate. And in a sense also for partial derivatives up to order alpha, where again alpha has to be less than n in this special sense. Okay, the proof of this theorem is really not so trivial. It's based on an embedding theorem in anisotropic Sobolev spaces. And you have to use the mean value theorem for divided differences, and so this is a little bit more advanced to show that. Here is an example showing you that this result is actually sharp, yeah? And it explains exactly where the problems come from, how the clustering of interpolation nodes affects the interpolation error. So let's start with this function on the unit cube, the unit square we are now to. It's x plus y to the power 11 over 2. Yeah? And the order is 5 in both directions. The estimate of our first result using these mixed partial derivatives does not apply because this partial derivative simply not exists. This is unbounded, so the theorem does not apply. Okay, now let's look at our better result using these least distances. We use the following sequences of interpolation nodes. It's 0, epsilon, 2 epsilon, 3 epsilon, and 1. So we have a clustering near 0. Epsilon is small and positive. It's easy to show that in this case, the interpolation error is unbounded. it's greater than 1 over 50 times the square root of epsilon. Yeah? So we should see that in our estimate. And indeed, if we choose, for instance, m, this is this pair of numbers telling us how to compute these distances. If we choose that as 2, 2, then this is admissible because 2, 2 is less than 5, 5 in this sense. If you compute the sum of the ratios, you get 0.8. But these least distances are both 1 over 3 epsilon, because if you skip 2 intermediate values, you get from 0 to 3 epsilon. So this is the this shows you that the least distances become, oh no, this should be 3 epsilon, not 1 over. This is a typo. The least distances are small, so that the constant becomes big. Yeah? And you see that here, it cannot be bounded independently of epsilon. If you choose m equal to 3, then these least distances are 1. If you skip the 3 interior nodes, then of course this is 1, this is bounded, but this m is not admissible. It's simply too big in that respect. Yeah? So it shows us that it's not possible to come up with a uniform bound in this situation. But now we take the same function, but in x direction, we take a 4-fold 0. So this is Hermite interpolation, 4-fold 0 and 1. And in y direction, we have a double 0, double 1/2 and 1. And here a computation shows that the interpolation error is bounded by 0.32. So this is, despite the fact that we have these multiple interpolation nodes, you get a bounded interpolation error. And this is verified by the theorem. If you choose m equal to 3 and 1, then this is admissible. Yeah, so m is less than n in this sense. And the least distances are 1 in x direction. If you skip 3 nodes here, it's from 0 to 1. And in y direction, this is 1/2. If you always skip 1 interpolation node from 0 to 1/2, from 0 to 1/2, or 1/2 to 1. So we have this type of clustering, which is admissible according to the theorem. Yeah, so 3 and 1 is fine, this type of clusters, but higher order clusters are not permitted. So this is, I think this explains fairly well how the interpolation error behaves on a tensor product grid. Okay, next part of the talk, if we are not interested in interpolation, but simply in the question, how well can a given function f, defined on some domain omega, how well can this function be approximated by a polynomial? No matter how you compute that, what is possible? Yeah, the answer to this question will depend on the subspace of polynomials which you choose. It will depend on the regularity of f, and of course on the geometry of the domain. But how? There's a very famous theorem by Bramble and Hilbert. It's called Bramble-Hilbert Lemma, but I think it's a theorem. In this famous result, it's stated if the domain has a Lipschitz boundary, and if the function f is in the Sobolev space Wn with exponent b, then there exists a polynomial p of total order n such that we get an error estimate of the expected type, the partial derivatives of order n and some constant depending on omega. It should be mentioned that the main work for the proof was done by a guy called Murray some years earlier. The proof is non-constructive, and the dependence of this constant c on the shape of omega is not specified. Okay, then there were many papers addressing this subject, and I'd like to sketch the development. A few years later, Dupont and Scott said, well, it's not necessary to have a Lipschitz boundary, but it's sufficient to have a star-shaped domain with respect to some ball. So in this case, every point in the domain can be seen from every point inside this little ball here. So star-shaped domains with respect to a ball admit the following estimate. The polynomial is defined as an average Taylor polynomial. The proof technique is similar to that for Sobolev embedding theorems. And what is great about this paper, the dependence of the constant on the shape of omega. Oh no, not yet, sorry. I confused that. In this paper, the constant is not specified. It's also simply an existence result. This was done 3 years later by a guy called Duran, I think he's pronounced. Again, we have star-shapedness with respect to a ball. And in this paper, the constant is specified explicitly, at least in principle. It's computable, this constant, in a given setting. Next progress was made by Deshevsky and Quark. They showed that it's sufficient to have star-shapedness, complicated word, with respect to a single point. So such domains are now allowed. And again, they are able to specify the constant explicitly, but the restriction here is that the exponent p, here for the LP norm, has to be greater than the space dimension. Next progress by Verführt, he improves that to p greater than or equal to 2. So now it's possible in L2. And a student of Verführt, Truhn, could show it for all p greater than or equal to 1. But still, what remains open are such situations. For instance, this case, these are simply two parabolic arcs. They define a domain. This is not star-shaped. Or here in this case, when you have a highly oscillating bound of your domain, you have a diverging constant. Such situations are not covered by these results. Okay, here is a theorem I found a couple of years ago. Here, the boundary of our domain omega consists of a finite number of axis-aligned graphs. So we have graphs over the x-axis and graphs over the y-axis in the bivariate setting. And it's not necessary that these graphs are Lipschitz or something. They have to be bounded, this is all, or continuous, this is all. And the second ingredient, your domain has to contain some box B of non-zero size. Yeah? In this case, we can define the approximating polynomial explicitly by simply finding the best approximation in the L2 sense on the box B and showing that this best approximating polynomial on the box B also provides a good error estimate on the whole domain. So in this case, you find an estimate of, again, of the optimal type. You have only the pure partial derivatives in the coordinate directions and constants depending on the geometry of the domain and the order n, of course. And in this theorem, the constant is computable in a very constructive way. So if you have bound on the ranges of these functions defining the boundary, then you can compute this constant explicitly. I think I should skip the proof because otherwise I'm running out of time. Perhaps only the following remark. It's based on the following lemma. If you have a domain which is bounded by a graph of a continuous function, then, and you know that the function is bounded on this lower part here, which is denoted by capital phi minus. Yeah? So on this box here, you have a bound on the LP norm, and you have a bound on the LP norm of the partial derivatives in this direction, in the direction of the graph. Then you can bound the LP norm in this upper region in terms of the bound on the lower region and the norm of the partial derivative in the up direction. Yeah. So this is a kind of, this allows you to control the error propagation from this part here to the whole domain. And if this is available, there's a recursive construction for the error estimate on the domain omega, which is bounded by in the requested way. You start from the box, and then you add to this box a part of the boundary in that fashion. Yeah, so a part of this box has to be inside. A part of this newly added domain has to be inside the already available box, and then you can show that the error cannot grow too much in the outside region. You do it here, and then you do it perhaps for this piece, and so on and so on. And if you are finished after a finite number of steps, then you get the desired result. The proof is a little bit technical, but this is the spirit of the proof. Okay, as a special case of this estimate, we can consider Poincaré's inequality. Poincaré means how good can you approximate a function by a constant. This is requested in many applications, this special case. And here, the best way how to construct the polynomial, the approximating polynomial, is by simply taking the mean value, the integral of f over the box B divided by the volume of this box. So this average value is the best constant you can find. And in this case, of course, you have the error bounded by a constant depending on omega and the LP norm of the gradient. This is a special case of the previous theorem, and this applies also to domains which are bounded by axis-aligned graphs. But here you can do more. It's even allowed to use diffeomorphic images of graphs. So you can warp these boundaries in the way you want. I will show you a figure in a second. Here. Yeah? So this is the axis-aligned graph, and then you apply the diffeomorphism so that you bend it in some fashion. Yeah? So now the boundary of the domain is allowed to have such a structure piecewise. Yeah? So for instance, this this domain here is now covered. This is the diffeomorphic image of an axis-aligned graph, of course. Okay, so this is now allowed and makes the range of applicability significantly larger. And again, we use this lemma concerning error propagation, but now the constant also depends on the condition of the diffeomorphism, which is simply the maximal norm of Jacobians times the maximal norm of the inverse Jacobians. Yeah? So this ends the picture, but again, in this situation, the constant can be computed explicitly. Okay, the proof proceeds exactly in the same directions. And now, once you found this result for the Poincaré situation, you can again proceed to higher order polynomials and derivatives. So if we are now considering, for instance, polynomials of total order n, then we compute the approximating polynomial pi by matching the mean values of partial derivatives. This is also a well-defined approximation process, easy to compute. And in this case, we get a Bramble-Hilbert lemma of that type, a constant which is explicitly computable, error bounded in terms of this constant times the seminorm, the Sobolev seminorm of order n with exponent p. This is valid for all exponents p greater than or equal to 1, and also here for all partial derivatives of order alpha less than n. So that way you find a substantial extension of the known results of these estimates of Bramble-Hilbert type. There are even more generalizations, like you can consider all kinds of filter continuous projectors on the polynomial space, more kinds of polynomial subspaces. Essentially, these subspaces have to be invariant under differentiation. They have to be closed under differentiation. Then they can be treated with this theory. But I want to skip these extensions. Okay, now third part of the talk. What about spline approximation? Approximation with tensor product splines. As mentioned before, there is this Darman-de-Vaucherer error estimate, which says that given a function f, you can find a spline S such that the error is bounded in this way. Pure partials in the coordinate directions, not spacing in the coordinate directions to the natural power, and then some constant c. But as I told you, this result leaves many questions open. How do admissible domains look like? The restrictions given in this original paper are extremely hard. And also, as mentioned before, this constant depends on the aspect ratio of the grid cells, which is kind of unnatural. Why is this unnatural? Let's assume that we are given a uniform grid, a grid with 1 in all coordinate directions. Then this constant c has a finite value. And now we start to subdivide only one coordinate direction. So we start to subdivide, to refine the knot sequence in x direction. It's getting finer and finer. So of course we are proceeding to richer and richer spaces of spline functions. Every new spline space is a superspace of the former one, so the approximation should become better and better. At least it should not become worse. But here the constant c says, no, this is not bounded. This will grow because the aspect ratio is getting poorer and poorer. And this is kind of counterintuitive. Where do the problems come from? It's easiest explained by means of a 2D example. In this case, the domain is not convex. And here you see, say, if I use in x direction constant B-splines order 1 and some B-spline in order of arbitrary order in direction y, then we have only one B-spline which is responsible for this red shaded region. Yeah, but these the relevant parts are disconnected. So, for instance, the value of the given function could be 0 here and 1 here, and this one segment, this is one B-spline, cannot take good care of both parts of this function. Yeah. The idea to settle this problem is to use so-called diversified B-splines. This means that you use one copy of this B-spline for this component and an independent component, no, I should say an independent copy of this B-spline for that component. Using this approach, you get a richer spline space, which separates disconnected regions inside the support of a given B-spline. And indeed, these diversified B-splines have nice properties. To start with, here's a restriction. This works in 2 dimensions. In the bivariate case, if the domain is bounded by a finite number of axis-aligned Lipschitz graphs, then you can find a constant c which depends only on the order and the geometry of omega, such that the optimal error estimate applies. Pure partials and powers of h. Yeah. Again, this constant. I should put it that way. In this estimate, the constant c does not depend on the aspect ratio. This unnatural dependence is now removed, and it's exactly achieved by using these extra copies for disconnected parts of the domain. Yeah, so this is kind of the best error bound you can hope for. But here's the restriction. This is valid only in the bivariate case. Of course, there are many important applications where you are in 2 dimensions, but what happens in R3? Here is a counterexample. The domain omega is bounded by an algebraic surface. So here is the equation. You see a degree 4 polynomial, and this domain is, the bound of this domain is as smooth as it could be, and it's convex. So this is kind of the optimal situation. Now let's choose order n, so it's equal in all directions, and n should be at least 2. And now we choose the following knots. In x direction and in y direction, we use the knot sequence h times z. And in z direction, we use a very, very fine knot sequence, h to the 5 times z. So our the aspect ratio again is very high. We have tiny little values in z direction and relatively large sizes in x and y direction. And now here is a special function which should be approximated. This function depends on h in the following way. We have a polynomial, and you see it here, some exponential function and so on. And for this specific function, you can show that the approximation cannot be better than this expression here. You see again the typical structure of the error estimate, but now this constant has h in the denominator. So as h tends to 0, the constant or the factor in front of the sum is exploding. And there's no way to get rid of that. Diversification does not help, and all the other tricks are not applicable as well. So this shows us that the 3-dimensional case is actually much harder than the bivariate case. So typically there is a jump in complexity when you pass from 1 to 2 dimensions. But here there is an extra jump when you go from 2 to 3 dimensions. Something is going on here, and I don't know where this is coming from. I simply know that these are the facts. You cannot expect an estimate, an error estimate with a constant independent of the aspect ratio in the 3 variate case. So here's my conclusion. I think it is necessary to understand approximation properties of polynomials and splines better when approximation is done on domains. The case of approximation on boxes is analyzed in any detail, but for applications like simulation and so on, domains are not boxes. Domains have some shape, and we should be able to use we should use the power of splines for these situations, but only a better understanding of the underlying theory will narrow the gap between approximation theory in theory and approximation theory in practice. Yeah, so more basic research is required, and yeah, I hope that I could make you interested a little bit in this subject. Thanks for your attention.
Let's thank the speaker for a very interesting talk, and we proceed to some kind of questions. And maybe I will ask the first one.
Yes.
Concerning the second part of your talk about this Poincare type inequality. So in your theorem, there is some box called B, yes? And the method of approximation depends on this B. So we choose coefficients of polynomials depending on this B, and the estimate also depends on this B. So it's
yes,
and it may be some very, very terrible dependence or what. So
I think I understand your question. The point is, if this box B, which has to be contained in the domain, is very small, then the constant explodes. Yeah, and this is necessarily the case. You can show this by examples. If this box is relatively large, the constant is getting smaller. Yeah, so this is necessarily the case. If you consider a domain which is very thin in a sense, so that it contains only very small boxes, then you can construct examples where the polynomial is not able to find a good approximation. Yeah? So this is in the paper which I wrote on this subject, there's an example discussed in some detail, which ends up with a specific number for the constant. So say the constant is 27. And you can find a concrete function, and you compute for this special case the constant, and you will see that it's perhaps 10. Yeah? So the constants which are computed by my method are not away from the truth by orders of magnitude, but they are fairly reliable in a sense that you cannot be much better. Of course, you never reach the optimal constant, but it's in the same order of magnitude.
So, and there are some possible corollaries, yes, when this dependence is stated explicitly on this.
Yes, it's stated explicitly, and you can, in the way how you construct the whole domain starting from the box, you add details and details and details. In every step, you know exactly how the constant will grow. So this can be done by a human being, also by a computer. All that you need are bounds on the ranges of these functions describing the boundary.
Thank you. Are there any questions? Any other questions?
Can I ask? I have a couple of questions, actually.
Yeah.
So my first question is on the result of polynomial interpolation in star-shaped domain with respect to a ball.
Yeah.
Are there I don't know, some extensions, some relaxes of this condition? This condition, for example, I don't know, maybe it's star-shaped just with respect to a point, but Lipschitz, for example. It should be some advantages from this domain, yeah?
So in this result of Deshevsky and Quark requests only star-shapedness in the usual sense with respect to a single point, but then you don't need Lipschitz. It's only about the range of the function.
Am I correct that it's automatically Lipschitz? No?
No, it is not. I will show. Wait a second. I will show you the corresponding figure. This one. This is perfectly fine, and you see these spikes can be as sharp as.
It's not with respect to a ball, yeah.
No, this is respect to a single point.
The single point, of course, but I think with respect to a ball, yes, it's automatically Lipschitz, yeah.
Yeah, you're absolutely right. This is a consequence of being star-shaped with respect to a ball. Then you get Lipschitz boundary, and Lipschitz boundaries were already addressed by in these earlier papers. But the progress that was made is the explicit specification of the constant, which was able in these situations.
Yes, but my question was star-shaped and Lipschitz, but star-shaped with respect to point. How do you think? Is it could it be true that this will also give some estimate for the constant? No.
I think that you cannot improve it. Essentially, I have the impression that the smoothness of the boundary is it simply does not matter. The boundary regularity is not the crucial factor. Yeah, it's about the ranges of these functions. They vary between a lower and an upper bound, and the ratio between these bounds is crucial in a sense. This is my impression. It comes from exactly that. Or if you start to bend it using these diffeomorphisms, the the non-linearity of these transformations is also crucial. So if you deform it very, very strongly, then of course constants will get bigger.
Mm-hmm. And one more short question, if you don't mind. In some problems, people are interested not in polynomial, but in exponential polynomial approximation. So if we have a quasi-polynomial, the sum of several exponents, even, for example, with real powers, with real exponents, it seems that at least, of course, you showed us only ideas of the proof, so without details. But do you think your method can work for these exponential polynomials also?
Yes, definitely.
Yes.
Because all that is needed is the error estimate on the box. If you understand how good the approximation is on the box, then the control of error propagation will give you a result.
So basically it should work for tensor products of Chebyshev systems, of univariate Chebyshev.
Yes. I think this would be a general framework.
Perfect.
Where the method applies.
Thank you.
You're welcome.
Other questions?
Yes, I wanted to ask, maybe I missed it, when you consider in the first part of your talk the interpolation with points when we skip some points. Can we consider the coincide points? So am I right that if we do that, then the results change somehow, since if we skip a points, we obtain another one?
Say it again. I did not get your question exactly.
In your example, one of the examples, you considered the points which coincide in the first part with skipping points.
You mean this?
Yes, this one. And okay. I wanted to ask if it is sometimes reasonable to add these coincide points artificially to obtain some other interpolation estimation.
Yes, so I think the use of multiple interpolation nodes it can make a lot of sense. This Hermite interpolation can be useful in applications, and this result tells you that, for instance, in this case, it is not allowed to have high multiplicity both in X and in Y direction. Yeah, it explains exactly how the clusters can behave. And if you have high multiplicity in one direction, the other direction has to be more relaxed, and vice versa. Does this answer your question? I'm not sure.
Not exactly, but that's. I mean that there you have 2 points, 0 and 1/2, and 0 and 1/2, and so do we do interpolation by the point 0 and 1/2 in the same way but all other points?
I'm not sure if I understood your question.
Okay.
Can you try to rephrase it?
When I try to ask another one, also a short one, if the last part of your talk, you said the result in 3D, the last result which we discussed, and I wanted to ask if is some results with more strict restriction on the domain.
No. Okay. I think so. There are some results, again by Dahmen and Devaux, I think, where they have these, say, optimal results for a situation where the domain consists of a box with rounded corners. Now, say you have a square, and you are only allowed to round out the corners a little bit. And then you have the optimal estimates. But I think such special domains are of little interest, because if a method is not able to deal with such a really very smooth, very convex situation, then you should be careful with using these highly anisotropic knot sequences. Of course, the problem can be solved that way, that you don't use this extremely high to use knot sequence which are so different in the coordinate directions. If you say I use h in all directions, or in this case h and h squared, then it would be fine. What I'd like to know is it this was the simplest example which I could construct. So h, and h to the 5. I was not able to construct an example for h to the 4. I would be interested in understanding this. So is there a bound on the aspect ratio which is still admissible? Where do the problems start? I don't know. So this is one of the questions I'd like to understand better.
Thanks.
Other questions? So then let's thank the speaker of today's session.
Yeah.